Morning. Good Wednesday. Let me pull up our handout. I need to see where we were, where we stopped. I think we stopped with calculating oxidation numbers. So we're going to do one more example of that as far as um, determining whether or not a redox reaction occurred. I think we did two. We're going to do one more of that. And then we're going to jump into looking at some redox reactions and balancing them. And I'm actually working on a little tool to help you remember the steps for balancing because it's a lot, but we can do it. And hopefully I'll finish that today. That it's a short video, and I'll get it sent out sometime after so we can reinforce what we're going to discuss today. All right, so let's take let me share my screen. Yes, that's all right. Let's keep it raw. It's coming up. All right. So we left off looking at these reactions, and yeah, it's recording. Looking at these reactions right here. Did a redox occur? And we showed in the first one, no, because zinc didn't change oxidation states. So when a redox reaction happens, there's a necessary change in oxidation state. If it doesn't, nothing changes oxidation states, then there's no redox that has occurred. So let's look at one more of these examples. We did the zinc carbonate one, we did gallium. We're going to do one more and find out whether or not this is actually a redox reaction. All right, so let's take this one. Make sure my pen good. All right, so we're going to take H2O2, and we're going to break that up into H2O plus O2. Now, is that balanced? What's the date? The 30th. Right? Is that balanced as it is? That's not a 3, by the way. I apologize. I think I'm gonna go back and get some handwriting lessons. I know they got some workshops about stop using a stylus, this and that. I know they can somewhere. Anyway, is that balanced or not?
It's not.
It's not. How would you balance it? What would you do?
I'd put a 2 in front of H2O and in front of H2O2.
Okay. So let's think about that. So the hydrogens are balanced. Oh, sorry. And then over here, we got two hydrogens and 3 oxygens. So you want to put a 2 in front of here. Is that what you're saying?
Yes.
That's going to be times 2. That'll be 4. And then this is going to be 2 plus 2 because you got 2 here. That's going to distribute. And then 2 here. So that's going to be 4 oxygens. And then you want to put a 2 here. Is that right?
Yes.
Excellent. Excellent work. So this is times 2. That's 4. And then this is also times 2. That's 4. So now it's balanced. Great. And you can see again, everything hinges on balancing, right? You have to balance the equation before you can do anything with it, before you can gather any data from it, like stoichiometry, oxidation number, anything. It has to be balanced first. If it's not balanced, any manipulation or calculation or anything that you do is going to be off if it's not balanced. So now it's balanced. Let's see if a redox happens. So let's check the oxidation numbers on oxygen. And so let's solve for that. We know what it is, but if you have two atoms together in a molecule like that, you can actually just make one the unknown and solve for it. So for this one, we're going to solve for that. We're going to say that you see that is neutral. It's considered a polyatomic because it's more than one atom. So we're going to say that this is 0. That's the charge on it. Remember that from the other day. That's my charge on the whole thing. And then we know hydrogen, when it's bonded to a nonmetal, is +1. And we got 4 of them. So it's going to be 4 times +1. And this is going to be plus because they have to add up now. 4x. Is that right? All right. So in this case, we're going to say that 0 equals 4 plus 4x. And then so we'll subtract 4 from both sides. So that's minus 4 equals 4x, and x equals -1. All right. So in this case, the oxidation number for each one of those oxygens is -1. All right. Now let's look at oxygen on the other side. But we're going to look at this oxygen. All right. And we're going to look at this oxygen. So this oxygen, the O2, we could just set that equal to 0, right? We know that O2, we said that if it's molecular like that, then based on the rules, it has an oxidation number of -1. So we can't tell anything from that. But let's look at the oxygen in water, right? So again, if we take the hydrogens, so we have 4 hydrogens, so 4 times +1, and then plus 2x, is that right? And we're going to set that equal to 0. So this is the oxidation number for oxygen and water. So that's going to be 0 equals 4 plus 2x. And then that's going to be -4 equals 2x. So x is going to be what in this case? -2. Y'all following? Anybody not see that? Oh, hold up. I need my x right here. And start that around. All right. So now we see that the oxygen in water, right? Actually, did the charge go down or did it go up? If I go from -2 to -1, is that a reduction or is that an oxidation?
Oxidation.
Okay. Are you sure about that? Is -2 a bigger number than -1?
So you saying it went from -1 to -2?
-2, yes.
Oh, okay. So then it would be reduction.
It's a reduction. So oxygen, in this case, got reduced. So this is a redox. It's a type of redox reaction. So we'll say yes, it is a redox. And this is the reason why I'm doing it this way is because it's kind of, I'm gonna erase the balancing part. We did that already, and we're kind of familiar with that. And plus, it makes it look more cluttered. I'm just gonna put here that we check the oxidation numbers. Right, so oxygen got reduced. And again, the reason we're doing it this way is because it's really important to be able to look at a reaction and you don't know what's what So the easiest thing to do is to check the oxidation numbers. If you don't know, don't guess. You can check it and find out. And we have rules to help us find these oxidation numbers. We know that oxygen is normally -2. Sometimes it's 1/2, right? Sometimes it's -1, depending on the state. The molecular state of oxygen, like the one in O2 on the right and the products, those oxygens have an oxidation number of -1. If it's in a molecule like with water, it's going to be -2. If it's in a superoxide or a peroxide like H2O2, it's going to be -1. So it did get reduced. All right, now we're going to move on. And there are, oh, I don't feel like writing all this. Well, I'm gonna write it as we go. All right. So we're gonna now talk about balancing redox equations. And I wrote this somewhere in here, and now I gotta find it. I have to move it around. But let's talk about that now. That's the topic for today: balancing redox equations. So we know we have an idea of what oxidation reduction is. We know reduction is the gain or the loss. No, sorry, gain of electrons. Oxidation is the loss of electrons. We also know that, excuse me, oxidation could be an increase in oxidation number. Reduction is a decrease in oxidation number. So we know all these different nuances now for what oxidation and reduction is. But when we have these redox reactions, all of the information that we've learned up to this point, we're going to apply it now to what we call a redox reaction. So let me give you a first example. And off the break, there's some conditions for redox reactions, right? So this is the topic that we're doing right now, balancing redox reactions, right? And in this case, we're going to be talking about reactions either in acidic media or basic. We're going to do two. This is going to probably take up the whole class. It's either going to be acidic or basic. And then on Thursday, we're going to talk about stoichiometry. I'll try to have a short handout so we can work some problems leading up to stoichiometry, and then finish with stoichiometry on Thursday and Friday. That's a really concise topic. We'll be able to talk about that and work examples with no problem for stoichiometry. So these redox reactions that we're going to be talking about here are specific. They're either in acidic or basic solution, right? So let's take the first example. And let's look at it. So this is going to be dichromate with a -2 charge. And that's going to be plus iron 2+. And that's going to go to chromium 3+, plus iron 3+. All right. So the question is, what is the redox, how do I put this? The net redox reaction for this? How do we show this, right? So anytime you have a redox reaction, there are 7 steps that you have to go through. If it's basic, there are 8 steps, because there's a final step at the end that you have to do. It sounds like a lot, but we're going to work through each step, and I'll talk about what's happening in each step along the way. All right, so just buckle your seatbelts. But the video that I'm working on, I'm almost done with it too, by the way, is going to help you to crystallize this and put this in perspective. It looks daunting, but at the same time, if you know how to approach it, then it's not so bad. All right, so the first thing you want to do is write out the half reactions, what we call half reactions. And then the half reactions, what you're looking for is the species that are the same, right? So you got chromate on this side going to chromium, and then you have iron 2+ going to iron 3+. So we're going to pair those up, because each one of those is a separate reaction where something either gets reduced or oxidized. Always remember that too. If you're doing a redox reaction, but when something is being oxidized, something is also being reduced at the same time. All right. So with the half reactions, we're going to write it. One of them is going to be Cr2O7, and this has a -2 charge going to Cr3 plus. All right, because that's the chromium part of it. The iron part is going to be Fe2 plus going to Fe3 plus. Following? Everybody okay so far? This is where it helps to know the oxidation numbers too, because if you know the oxidation numbers, that helps us in one of the latter steps where you have to figure out how many electrons to add or subtract or whatever, or well, how many electrons to add either to the reductant side or the oxidation side. All right, so we write the half reaction. That's the first thing you have to do. Write out the half reaction. So we've done that. We took the chromium species and we paired them up, and we took the iron species and we paired them up. So here, let me write that as a, right, you're going to pair up like species. So chromium went to chromium, iron went to iron. So that's how we're going to approach that. Right. All right. Once you write the half reactions, then you have to balance all the atoms except oxygen or hydrogen. Don't touch those until there's another step for that. So in the second step, we're going to balance all the atoms. All right, balance all the atoms. So let's look at it. If how do I balance 207 minus 2 going to Cr3 plus? How do I balance that? Don't worry about the oxygen part, because there's a specific step for that in the third step. So again, third step, how do I balance this chromium? What would you do?
I'm sorry, I couldn't hear you. What'd you say?
I said, how would you balance chromium? We're not balancing oxygen yet. That's another step. Well, how would you balance chromium in this case? How many chromiums are on the left in the reactant side?
2,
2. How many on the right?
1,
So what would you do?
2 with the not a subscript, but what's the other word?
Coefficient.
Sorry, I'm walking. Yes, that one.
Yeah. You want to put a 2
I'm
right
walking
here.
through the farms. I'm sorry.
That's all right. I hear you. I hear nature calling, but we good. All right. So that's that. Is that right? God dang it. Stop that. I don't know why that does that sometimes. I think it happened when I dropped my iPad the other day. All right. What about the iron? Do I need to do anything with that? So this is Fe2 plus going to Fe3 plus. Do I need to do anything with that?
No.
No. I can balance the charges, but I'm not worried about that right now. I'll do that later. Right now I'm worried about the atoms. So balance the atoms. There's another step where you're going to balance the charges, what we'll do shortly. So balance all the atoms. We've done that. The third step is balance oxygen if it's present. With water. I like that too, because since water has an odd number, oxygen, it's got 1 oxygen. You just add as many waters as there are oxygens, but you add them to the other side to balance it out. So here we're going to do this. There's no oxygen in the second half reaction, so we're just going to write that again. Fe2 plus going to Fe3 plus, no problem. That top reaction, how many oxygens are in the reactants on the left side?
7.
7. How many waters do we need on the other side? Because remember, balancing, you're trying to get the same number of atoms on both sides. So you don't put the water on the same side where the chromate is, or dichromate. You want to put it on the other side so that there's 7 oxygens over there. So how many waters would I add? So this is Cr2. Come on, Russell. 07 minus 2 going to what? 2 Cr3 plus. How many waters? I need 7 oxygens over there. Go ahead.
Would it be 7?
7 oxygens. 7 waters. I need 7 oxygens to balance the 7 on the other side. So I'm gonna add in 7 waters to make that happen. Anybody feeling a little sick on the stomach? Ready to throw the towel in, or you gonna keep pushing? We gotta keep pushing. All right, so we balanced oxygen. Now the next step is to balance hydrogen. And you do that by adding H plus to both sides. All right. It's a very, very detailed process, but we can handle it. So the iron, there are no hydrogens present on either side there. So not worry about that. So we're going to just write that out. Fe 2 plus going to Fe 3 plus. Is that right? No, we don't have to do anything with that because there's no hydrogen, there are no oxygens. We don't care. Now on the other side over here with the chromium, how many hydrogens are on this side?
Would it be 14?
14. So I need 14 hydrogens on the other side because I'm balancing hydrogen. So balancing means both sides has the same number of atoms. So I'm going to add that in. 14H plus, all right, plus Cr2O7 minus 2. And that leads to 2 Cr3 plus 7 H2O. Any questions about that so far? It's a long process. There are 8 steps, but we almost 7 steps for this problem because you only need the 8th step if you're doing it in basic solution, and this is an acidic solution, so we're not worried about it. All right, so that's that. Balance the hydrogens with protons. All right, and then the next step is to now balance charges. Right, so there's 2 ways to do this. I'm gonna show you both because I think it's important that you know how to do it both ways. So you want to balance the charges with electrons. So you balance oxygen with water, balance hydrogens with protons. Remember, a proton is H plus, and then you balance the charges with electrons. So you're going to add electrons in. So let's look at what we have. All right, I'm just going to copy this because it's going to be the same thing, and I'll just have to move it around a little bit. All right. All right. Now let's think about this. There are 2 ways to do this step. You can add up all the charges, right? So this will be here. The charges is going to be, let me show you this way first. So that's going to be 14 times plus 1. And this is going to be 1 times minus 2 because the dichromate anion has a -2 charge. And the hydrogens all have +1 charges. So the total charge is +12 for the left side. Y'all following that? 14 hydrogens or 14 protons. All of them have a +1 charge. It's going to be a +14. And then the dichromate has a -2 charge, and that's going to be -2. So 14 minus 2 is +12. Yes or no? All right. I'm gonna take that as a yes. If it's a no, say something. Unmute, hit the hand raise button, put something in the chat. All right. What about the other side? What's the total charge on that side? What's the charge on water? If you notice, we're over halfway done with this example. We're on step 5 and we got 7 steps because this is acidic. Anybody? What's the total charge on that on the product side? If water is 0.
Would it be 3 plus?
How much?
3 plus?
Okay. And then you got a coefficient of 2, right? So you got to include both atoms.
Oh, okay.
So it'll be what? You're right. But you just need to,
6.
it'll be 6 plus. Following? I'm gonna say +6 like I did the other side. I don't want to make that look confusing. So 2 times +3. Right. This is the total charge for that side. Any questions about that? We're just all we're doing is adding up the charges on the atoms.
I couldn't hear you. That's what are we working on?
We're
That's
doing the total charge for each side.
gotcha.
Mhm. So the total charge for the left is +12. The total charge for the right is +6. Now, here's the question. I don't want to add, there's no way I can take +6 up to +12, but I can take +12 down to +6. How can I do that? What do I have in my toolbox that can make a charge go down?
You can add 6 electrons.
Add, I'm buying you lunch today. Add 6 electrons. That's exactly right. So we're going to take this side right here. I didn't mean to take the arrow. Move that over. And we're going to add 6 electrons here. And this is going to balance the charge. Following? Right? There's no way we can take +6 up to +12. We don't, when you're doing a redox, you don't touch protons. So you're not going to take away 6 protons to make it more positive. You either add electrons to one side or add them to the other side. So we balance that charge by adding 6 electrons to that side. Now let's do the other one, because the bottom one, we got a little problem there too, because iron went from 2 plus to 3 plus. What did it do? How did we go from 2 plus to 3 plus? The charge went up, didn't it?
So an electron was removed.
So you lost an electron from iron. That's right. And so the way you show that is to put that electron over here. It's Fe3 plus 1 electron. All right. So notice now, what happened to iron? Let's answer that question. Did it get oxidized or reduced?
Oxidized.
It got oxidized. So anytime I'm showing oxidation, the electrons are going to be on the product side, on the right of the arrow. So when oxidation, sorry, I'm getting excited. This is I've been thinking about this day ever since I read this section. But not, let me not say that. When oxidation occurs, the lost electrons are shown on the right. Let me say it that way. Right, so I'm trying to balance that charge of that oxidized iron. So I'm going to put the electrons on that side, because the other side, again, the charge went from 2 plus to 3 plus, right? So I'm not going to take 2 plus and subtract an electron from that. I'll just take the 3+ side and I just add an electron over there. So when I'm showing oxidation, I always put the electrons on that right side of the arrow. By the same token, what happened up top with the chromium? It looks like chrome got reduced. Is that right? Because well, not chromium, but the chromate, the chrome and chromate got reduced because we added 6 electrons. So this is the reduction side over here. So we show the electrons on the left. So when reduction occurs, you show the electrons on the reactive side, right? The right is the product side. Let me put that in here. I'll write it down here. Show the electrons that got gained, you show that on the reactant side. All right, questions about that? There's another way to do this. And that would be if we were looking for chromium to see if it got oxidized or reduced, we could easily check the oxidation numbers, right? So we did the method one, we just balanced the charges by adding up all the total charge. But the other method would be to look at chromium. Right, we can look at the iron and easily tell that that's oxidation because the charge went from 2+ to 3+. But with chromium being in that polyatomic dichromate anion, that's hard to see, right? And so we could actually take the chromium. So we'll check it for Cr2O7 -2, and then we know what the oxidation number is. Here is 3+. We got 2 of them, right? So here we're going to set that equal to -2. That's the whole thing. And then we're going to solve for chromium. So this is going to be 2x and then plus 7 times -2, which is for oxygen. Following? This is oxygen and this is for chromium. And now we're going to determine the oxidation number for chromium. Right? So this is -2 equals 2x minus 14. So -2 plus 14 equals 2x. Minus 12 equals 2x. And then, so this is -6 equals x. Following? So chromium, in this case, is going to have a, hold up, that should be plus 12, not -12, my bad. +6. So chromium has a +6 charge. And since there's 2 of them, that charge is +12. So then that means that the other side, this has what? This is +6 because it's 2 times +3, right? So that's +6. So then now you can see this is +12, +6. So I need to subtract or add 6 electrons. So that's the other way to do it. Whatever way you feel comfortable with is fine. But again, checking the oxidation numbers means that you can go in and look at the individual atoms and say, okay, this atom got reduced because it started out, the 2 chromiums were +12 and then they went to +6, right? So that's another way to think about that. All right, let's go to step 6. Are there questions about that before we move on? Not bad. All right, so the 6th step is now we've done balancing charges, we've balanced hydrogens, balanced oxygen, done the half reaction, balanced the atoms. Now the next to last step is to balance the electrons. So that's step 6. So balance the electrons. I'm gonna steal this from up here. So this plus 6 electrons. Russell, tighten up. And it was this plus 1 electron. All right, now here's the question. How would you balance, what would you do to balance the electrons? Right, you got 6 in the top reaction, top half reaction. You got 1 in the bottom half reaction. What would you do? I want the same number of reactions, same number of electrons in both reactions. And I got 6 here. And I have 1 here. What would you do there? What would you do if that was an atom and you needed 6 atoms on both sides? What would you do? All right, we can actually take this whole thing and multiply through by 6. So everything gets multiplied by 6. So now this becomes 6 Fe2 plus goes to 6 Fe3 plus 6 electrons. So multiply everything by 6. Yes or no? Because what I'm trying to do is balance my electrons. So if I have 6 on the left side, which is the top reaction, and then 1 on the right side, the bottom reaction, I need to balance them because at some point in the next step, I want to cancel them. I want to get rid of them. Right. So I need to make sure that there's the same number of electrons on each side so I can get rid of them at the end. All right. Any questions so far? Y'all got quiet. Everybody got quiet. All right. So the last step is to add the half equations and cancel what you can cancel. I'm just going to add them together. And then you're going to cancel anything that's common to both sides. So let's bring this down. And let's bring this one down because now that's what we're working with. All right, so anything on the left side of the arrow, we're going to add together. So all of this stuff is going to get added. I'm going to add all this together right here. And then anything on the right side of the arrow, I'm going to add all that together. All right. Is that right? So the left side now is going to look a little bit different because it's going to be everything, right? So I'm going to write that in this color right here. So it's going to be 14H plus plus Cr2O7 minus 2 plus 6Fe2 plus 6 electrons. All right. And that is going to give me what's on the right side. 2Cr3 plus 6Fe3 plus 6 electrons plus 7 waters. So that's the sum. What's common to both sides? So what species is common to both sides? Is there anything that both sides have in common? That's what we want to get rid of. And then once we get rid of that, what we have left is going to be our final redox equation. What can I get rid of?
The 6 electrons.
6 electrons. That's the same on both sides. So let's do that. Let's take it here and here. We can get rid of that. Common to both sides. And then we're going to write the final redox equation like this: 14H plus Cr2O7 minus 2 plus 6Fe 2 plus yields 2Cr3 plus 6Fe3 plus 7 H2O. That's the final redox reaction. It's a lot of steps. I know that, but if you can do this, you can do anything, and you can do it. It's just practice and reps. I have another example, but I don't think we're gonna have time to get through it. But let's go back and analyze this because I want to ask a couple of questions. So up here.
You leave the one screen up just so I can write the answer down.
Oh yeah, right here. Right. Let me put a note in too that this is the final redox equation. All right, so this is done in acidic solution, as you can tell by the H plus. Sometimes the actual problem will indicate that it's in acidic solution. Sometimes it'll say it's in basic solution, and there's a totally different. Well, let me take that back. The basic solution, if it's done in basic solution, that's just an H step, which is to add hydroxide to each side to use up the protons. And then you'll get water, and then you get rid of. We'll do that example on tomorrow. I don't want to push it because if we start it, we're not gonna be able to finish it because that's a longer process, right? But let's go back and ask some questions about this. What is, in this case, if we go back to step 5, which one of these is the oxidant and which one is the reductant? Let's go back. I'll come back to that. So we'll leave it. All right. If we go back to step 5, actually not step 5. Yeah, step 5. Which one of these is the reductant? And which one is the oxidant? The oxidant is what? I gave you that definition the other day. What is the oxidant? Is it the one that gives up electrons, or is it the one that gains electrons?
The ones that gives up.
So the oxidant is that. Think about it. The oxidant is the one that actually loses electrons. Okay, I'm sorry, gains electrons. You said gives up electrons. The one that gains electrons is the oxidant. What? Hold up now. Right? The oxidant is the one that gains, that loses electrons because it's giving up electrons to another atom. Let me make sure I'm saying this right.
Right, because I'm like, hold on
Yeah,
now.
yeah, yeah.
Does it
So,
gain
so
or does it lose?
the oxidant is the one that causes reduction. So it's the one that gives up electrons so that the other atom can get reduced. Is that right? Or is it the other way around? How did we say that the other day? We said that the one that gains electrons is the oxidant, and the one that loses electrons is the reductant. That's it. So the oxidant is the one that got reduced, and the reductant is the one that got oxidized, because the oxidant is the one that's going to take electrons from an atom that's being oxidized, and the reductant is the one that's going to give up electrons to the one that's being reduced. That's it. My bad. All right. So in this equation, which one gave up electrons? Was it the chromium or was it the iron? And you can tell that by looking at which step is oxidation and which step is reduction. That's why I said when you show reduction, you want to put the electrons on the left side of the arrow. When you show oxidation, you want to put the electrons on the right side of the arrow. That's on purpose. So you'll know what got oxidized and what got reduced. So iron got oxidized. So by default, because it's the one that got oxidized, it is the reducing agent because it's giving up electrons so that chromium can be reduced. So iron is my reductant. It's the reducing agent, even though it got oxidized. That means it gave up electrons. Chromium is the oxidant because it accepts electrons. Notice it's +6 electrons with that chromate. So that's the oxidant. The dichromate is the oxidant, and iron is the reductant. I know I was just talking in circles, but I think we got it. So when iron gives up electrons, those electrons are used to reduce the dichromate ion. So that makes iron the reductant. When the dichromate accepts electrons from iron, that makes it the oxidant because it helps iron to get oxidized. All right. I know that was a whole spaghetti, what they call a word salad. But the point is that iron is my reducing agent and dichromate is my oxidizing agent. That's the point I'm trying to make. All right. Is that right, Maya? Are we on the same page now?
I think I'm good. I think I'm good.
All right. I apologize for the initial confusion, but it is confusing when because you're thinking oxidation and reduction, but then you got to think also in terms of what's causing oxidation and what's causing reduction. So the thing that gives up electrons is also by default giving them to something to reduce it. And the thing that takes electrons is taking them from somewhere to be reduced. So that's how that works. All right, so we're gonna stop here. This is a long thing, but again, when I finish the little video, hopefully that'll help you to remember the steps and how to attack these types of problems. And then we'll come back on tomorrow. I got to put a handout together for us for tomorrow, and then we're gonna work through some other examples leading up to the redox stuff, and then on Friday we're gonna cover stoichiometry because I think we could do that in a day. It's not something new. It's actually old stuff with a new application. All right. Any questions about anything?
This is still just chapter 4, right?
Yes. But if you look at this chapter 4 and other books, they'll split this into 2 chapters. Like there'll be a whole chapter on redox reactions, or at least a half a chapter. But it'll also be included in a different set of concepts. So this chapter 4 we've covered balancing, writing equations. We've covered different types of reactions, precipitation, redox reactions, acid-base reactions. And then the last part of this is stoichiometry, which is not going to be a lot because we already know about the relationships and with the coefficients. All it is applying them to different stuff. And I promise you, it's not going to take we'll take a half a class. We can take a half a class and do that because all old concepts, just with a different perspective. All right. Anything else? I know we got to go. We 4 minutes over time. All right. So we'll be back on tomorrow. I'll have a handout. I'll post it later and all that stuff, but you'll get an announcement from me. All right. Y'all have a good day. And okay, go ahead, Ortega. My bad. I just saw you had your hand up.